First, I'd like to thank Andreas and the organizing team for inviting me and for allowing me to speak, and all of you for coming. As Andreas said, I'm part of the local crowd here at Berkeley, so if anyone has any questions, I'm also happy to help and answer. Is this loud enough for the people in the back? Okay. So, no? Louder? Oh. Yeah, let's. Yep, that's good. So I'd like to talk to you a little bit about sort of scientific computing from the perspective of what I think is happening in the world of data science with respect to programming languages and tools. First of all, by California state law, I have to put this slide up. Anything good I say about any of these companies, please take it with a grain of salt, because in one way or another they support my work. But as regardless of the discipline that you're coming from, you're probably facing the fact that you have a ton of data, whether it's experimental data, sometimes it's simulation data, whether it's physical instruments like the LHC or the LSST, the biggest telescope that the NSF is building right now, or even your own. This is data from I suffer from sleep apnea, and this is data from my sleep apnea machine. And terabytes and petabytes of data that are flooding whose volume and complexity continues to grow are still feeding into the one thing that's not changing, which is your brain. You may have your little trusty laptop. You may have one of the world's biggest supercomputers. I don't know. I didn't read the top 500 new list. This is Cori, the newest machine up at LBL. It used to be number 5. Now we're number 6. Sorry, Roland. Such is life in the top 500, I guess. And what IPython and Jupyter have tried to do over the years, these projects, is really try to build a bridge between these large computational resources, or small, the data that you're trying to understand, and the fact that you still have only one brain. And so we try to give you tools to think and to reason about computation and data, independent of the programming language over time. And things began, as Andreas mentioned, for me back in 2001 when I was doing a PhD in particle physics, and I started trying to transition away from a tool chain that in my case was based significantly on IDL, which is a programming language that some of you who have backgrounds in physics or astronomy may be familiar with, also in remote sensing and medical imaging. We used it heavily in my group, and I wanted to transition to using open tools, to using open source machinery as much as possible, and also to have a fun procrastination project instead of finishing a dissertation, which is always an important thing for a grad student to do. And that became IPython. At the beginning, it was an interactive terminal-based tool. I think this thing is dropping. We'll see how this goes. It was an interactive terminal-based tool that really was aimed at the workflow that I needed, which is probably familiar to many of you, which is you want to run a little bit of code, you want to look at some data, you want to plot something, you want to be able to look at your files, you want to switch back and forth. I know the Julia REPL today has some really creative ideas in that regard, and I think it works phenomenally well. Back in 2001, I was trying to switch over to Python, and Python has a REPL. Python by default has a REPL, but it was a fairly primitive REPL from that perspective, from the perspective of actually having kind of a workflow that has code, your data environment, your file system, etc., your operating system, and potentially plots and interactive analysis. It wasn't really aimed at that. So this is how IPython was born. I want to make sure that I make it very clear that anything that I'm going to say about the project today is the credit goes to a huge team that does all the work. These are just some of the sort of closest developers to the core of the project. For pictures from our last two all hands meetings. I think there may be some in the room. Carol Willing, are you here yet? No, she hasn't arrived yet. And we have, and these are really the people who make it all possible. And just like Julia, a long tail of phenomenal open source community contributors. And we do get support from some of the same usual suspects that you do, like the Moore Foundation and the Sloan Foundation. We also have very good partnerships with industry, and I want to acknowledge that because the development of these tools over the last 10, 15 years has been this interesting back and forth between academic work done by scientists in places like national labs and research universities, and industry. Over time, the idea of having this terminal-based environment was not the only thing that we had in mind. I was a heavy user of systems like Maple and Mathematica when I was in physics in grad school, and similar systems I'm sure many of you have used. And so the notion of combining my analysis in a persistent manner, combining the analysis in a persistent manner in something that could be represented as a document and that could contain both the code execution and the narrative that goes along with it, and where the results could be stored in one place, that's something that was at the forefront of our minds from the very beginning of IPython. It took a while, it took multiple iterations. This is not the time to kind of go into a detailed story of it, but suffice to say that around 2011, after multiple prototypes, over the summer, Brian Granger was able to build, yes? Feedback? Okay. Was able to get basically the version that stuck of a prototype that would allow us, using web technologies, would allow a small team to build a system that would effectively give us what we wanted. The combination of documents, mathematics, computation, and the results of those computations, accessible through the web. Gmail and Google Docs and the Sage notebook had shown by that point that it was viable to build something like this with a web interface, which gave us the advantage that the same tool could run locally or remotely, which meant that you could be accessing a machine like Cori up at LBL and do it through the same web interface that you'd be using on your laptop without any sort of X11-based style shenanigans to be made, and that we could piggyback on the vast resources of the web development community, which is obviously far larger than the scientific computing community, and that we could basically reuse everything that was happening in that community regarding interfaces, etc. So the IPython at the time, called the IPython notebook, stuck. People loved it. People started using it, and it became clear eventually that it was going to be something for much more than Python, because at the time what we did was we basically broke off the execution of code interactively into two pieces. A client where you would interact, where you would type, where you would get your answers. That could be the terminal, or it could be the web browser, and the execution itself could happen in some other process. We defined a protocol for those two things to communicate. And once you think of it that way, whether you're sending Python code or R code or Julia code or Bash or Ruby or anything else, doesn't really matter, because you can effectively parameterize over the programming language, as long as on the back you have something that can communicate over that protocol. And so that's exactly what happened. Eventually we realized that the community would need something that would not just be called IPython, because the Julia team wouldn't want to be typing IPython forever, even though at the beginning the way to run Julia in IPython was IPython -- profile Julia. Similarly, the R team or any other team. This is a quote from a blog post made by Alyssa Frazee. She was quoting me at a meeting that the R OpenSci project hosted at GitHub in 2014, and we were chatting about, oh, Julia and Python and R, and I said, Julia, Python, and R are not enemies. What we're after is really closed source science, and what we want to do is build platforms for open science. And I was at PyCon a few weeks after this, preparing a talk, and I read that blog post, and I thought, Julia, Python, R. Julia, Python, R. For about a year by that point, we'd been looking, maybe 2 years, we'd been looking for a better name. And so I shot an email to the team and asked them, what do you folks think of renaming the parts that are not Python specific to be called Jupyter? It's not an acronym. It's not that it's only for Julia, Python, and R, but it was inspired by those. And we talked directly. So the team that we actually consulted at the time was the Julia team. This is an email that I sent to Jeff, Stefan, Yahao, and also Brian Granger, and Steve Johnson. And right away, Julia was kind of recognized as one of the drivers of the creation of the name. And there was also kind of this notion that it had resonances with astronomy. Galileo, the story of Galileo as being a scientist who built his own tools and who published the first publications about his discovery of the moons of Jupiter were actually effectively what you would call the 16th 1617 equivalent of modern notebooks. He had the narrative, and he had the plots, and he had the data, and he had everything. So we had kind of a good origin story, as Stefan said, about why this could be potentially a good name. This had been really prompted by the fact that in 2013. Stefan Karpinski and Jeff Bezanson spent a week while we had one of those dev meetings that I just showed pictures of for the Jupyter project, when it was much smaller and when we could all fit into one small room at Berkeley down in Tolman Hall across the other side of campus. They came over for a week. We had the funds to support their travel, and basically as we were in one table on one side of the room continuing to work on Jupyter, they were basically hacking up a kernel, and they could just come over and ask us questions, because this protocol that I spoke of at the time was underspecified and underdocumented and had only been tested for n equals 1, which was really Python. So we needed to know, well, does it really scale up to a second language or not? And this is a picture. I don't remember. I think this is Steve Johnson's laptop. I don't remember exactly. And unfortunately, if you zoom into that screenshot, you can't really tell that it's a Julia kernel, because the expressions that were typed in that first session of the kernel were things like 2 + 3 or hello world, which would be the same in Python or Perl or just about any language. Right, there was nothing that was Julia-specific syntax being typed by accident, but the editors that are open are actually showing the code of the kernel, and so. This is when this was kind of the meeting that kicked off the notion that a project like IPython, which was born squarely in the Python world, should become something bigger that would think about other programming languages. Because at the end of the day, what we're focused on is science, right? We're not really, I love Python. I actually really, really, really love Julia. I think it's an absolutely beautiful and phenomenal piece of work. But ultimately, languages are tools. And what I'm interested really is in facilitating scientific research. So yes, we have Python, we have Julia. There's a lot of fantastic work being done by statisticians in the R community. But over time, once we made this change to a project and we really worked, and the collaboration with the Julia team was essential, not only the creation of that kernel, but in filing off all the rough edges that existed and all of the inadvertently baked in assumptions about Python that were throughout the tool, in the notebook, in the protocol, in the messaging specification, etc., then the community kind of picked it up. And yesterday I counted, and now there's about 90 kernels for the project Jupyter that were basically, you can put in the back end something else. I don't think it's 90 programming languages. There's some repeated kernels for the same programming language, and not all of those are production quality tools. Some of them are kind of just afternoon projects. I was just counting on the wiki page where people say, I made a kernel, here's the link for it. Some of those are absolutely robust production tools. Others are probably just simple toys. But the point is, the community has embraced this idea that we can have a layer which is open and interoperable, and then another piece where each programming language kind of plays its role. Because programming languages have a long life. This is a check using the clock tool, counting lines of code sorted by programming languages of the SciPy repository on GitHub, the main repository for the SciPy library, which is kind of core of the scientific computing in Python, done from master yesterday. And so you see that there's a ton of Fortran 77 code, no surprise there. SciPy was born wrapping a ton of the classic netlib Fortran codes. There's a ton of Python there. There's C, there's C++, and obviously there's a lot of Python as well, no surprise. Julia has a lot of code also in not only in Julia, and though I understand and fully subscribe to kind of the message that Julia sends, that by making a very small core in Julia, in C, and the Lisp engine that you folks use for the parsing, you can empower scientists to basically use the language itself for the vast majority of the work, and that's reflected in these statistics. I have no idea what that robot framework is, by the way. Somebody can tell me later what they think that is. This is a straight up, I just did a straight up checkout of the repo, and I ran clock on it. That's it. That's what comes out. I have no idea what it means, and I didn't have time to track down what that meant. It's interesting that this really does bear kind of the idea that Julia is significantly written in Julia itself, and that the core project, because the MATLAB and Fortran 90 files that appear there's a few of them. I checked those. I went into the source tree and looked, and those are purely in the basically performance and benchmarking subdirectories. So you basically seem to have them there just for benchmarking purposes, which makes sense. Whereas on the SciPy side, the Fortran is part of the core, right? SciPy is basically a big Fortran project. But the point is, scientific ecosystems are not, even in the case of Julia where this model does work well, and I think that story is a story worth continuing on. Languages do have a long life. They persist. This is data from, and there's a Jupyter notebook to reproduce this plot made by Thomas Robitaille, who's one of the core developers of the AstroPy package. Which is sort of the Python cousin to the Julia Astro package that some people here at LBL have had a hand in developing. I imagine there's some of you in the audience. And this is the citation count. Remember I mentioned IDL when I was in physics. I was trying to basically get rid of my own IDL workflow. IDL has been the dominant language in the astronomy community for a really long time. And only very, very recently did Python surpass IDL, at least in terms of citations in the refereed literature. And this is after the Hubble Space Telescope team had been a core supporter of scientific Python more or less from day one, right? In the very earliest SciPy workshops that were smaller than this, the Hubble Space Telescope already had people working on the scientific Python ecosystem. They funded the first iteration of a package beyond numeric. What became NumPy was a project called NumArray funded by them. They funded Matplotlib's birth. They were funding a project with Nthought for plotting called Chaco that continued to develop as an interactive plotting library. So despite the heavy investment from projects as significant in astronomy as the Hubble Space Telescope, it took 15 years to transition, and IDL still has a long tail. So programming languages continue to exist and continue to coexist in ecosystems. And one of these days, we may all end up writing JavaScript, especially if some folks in that community have their druthers. This is the abstract or the description of a talk that was given. I didn't attend the conference, but I found it online at CSVConf, which was held last month in Portland. And the author is firmly convinced that JavaScript is the future of scientific computing, and that all numerical codes will be written in JavaScript in the future. I suspect some in this audience may disagree with that statement. Nonetheless, I just want to put it out there, right? Because there is a ton of JavaScript being written, and there are actually reasons why JavaScript can be a very valuable tool. I don't like to go bashing tools. I think there's valid reasons why people choose their tools, and we sort of have to respect that. And also JavaScript has the advantage that it really does appear in the client for free, with engines that have been optimized to death by really good people. And so I don't think the statement, despite all of the phenomenal work of the Julia community and R and Python communities, I don't think the statement is completely without merit, because I'm sure that over the years codes will be written in JavaScript that will probably have high numerical performance. I don't think all numerical computing will be in JavaScript in 10 years, but there will be some of it that will be done in JavaScript. And this fellow has a project called to build a standard library for JavaScript, but with a numerical computing focus. And I went and looked, and it's a large effort. It's a pretty serious effort. It's large. I didn't look at the code in detail. I just had a quick glance at the GitHub repo, but there's a fair amount of work being done there. And Sylvain Corlet, who works closely with us on the Jupyter team, recently wrote a blog post with a very similar title to the one of my talk. We were talking 2 weeks ago when we had our dev meeting. He develops a library called Xtensor, which is a library in C++ that precisely aims to enable numerical computing interoperability, taking the very best of the C++ 11 standard. If any of you have ever worked with a library called Blitz by Todd Feldhuisen from Indiana back in the kind of late 90s, early 2000s. It's sort of a modern reinvention of Blitz. It's a template. It's an array expression library that uses expression templates. It's a header-only library that gives you very good control over temporaries, very expressive programming in C++, and it was designed from the get-go to give you really good support in both Python and Julia, and I think he's working on R support. So for example, if you have a little bit of C or C++ code, and I do know that Julia has Julia makes it exceedingly easy, even easier than Python, to access C codes live, but Extensor makes it really, really straightforward, for example, to take a standard scalar function that computes some quantity in C++ and make it with one line of code, expose it as a Julia vectorized function automatically. And this may actually be really useful if you're in a world where you are dealing with a 500,000 lines of C++ code that has been optimized and is running at a large supercomputer. You're not about to rewrite all that in Julia, right? As I said, those codes have a long life, and so tools that help us cross these bridges, I think, have a lot of value. And as I said before, I don't know where the hum is coming from.
The feedback. Just continue.
Okay. And timing-wise, it's until 9:30, right? 9:20?
You have 25 minutes.
Okay, perfect. More than enough. Thank you. So, as I said earlier, one of our key goals in all of Jupyter is really to give people tools to make science open, more collaborative, more accessible, more reproducible, where the languages are just tools. And I want to kind of emphasize this point by bringing up a quote that I use often that some of you may be familiar with. This is from David Donahoe. David Donahoe is a statistician, and I think of him as a numerical analyst / statistician because a lot of his work is really in applied mathematics. And David Donahoe was doing all of his work in MATLAB at the time, so I haven't talked to David recently. I would imagine he would at some point make the transition over to Julia because he's a heavy-duty MATLAB user, and Julia, I think, is a very familiar and easy path to transition into for MATLAB users. But David wrote this as part of the manual, a paper that was the manual for a package called Wavelab for wavelets, for signal processing with wavelets. The point is, this was written back in '95, and it was a statement, I think, of intent that wasn't really very widely adopted in the late 90s and early 2000s, certainly not in the applied math community, where it was completely acceptable for a very long time, and still a little bit today, but less and less so, to publish papers that were considered completely viable with not a trace, not a hint of what you actually did to produce the plots, or the source code or the environment or anything else, and which in practice made it impossible for anyone to replicate your work, because there was probably a year or two's worth of implementation work behind those figures. And I say that as someone who did that and was not proud of it, but that was the standard of practice sort of 10 years ago. And so I think what we're seeing is that it's now possible to sort of embody the statement that David Donahoe made in the 90s. Now we do have the machinery to make this possible. So this is an example of a paper that we published with a colleague who's now at UCSD. This is analyzing microbial community data in computational biology. Rob is one of the leading developers and leading scientists in the world of microbiome research. And what we did was we took their analysis, parallelized it, optimized it on Jupyter, IPython at the time called, put it in the cloud to make it accessible. But we didn't just publish a paper in this journal. What we did was we actually offered the notebooks and the configuration file. If you zoom into the screenshot, obviously you can't see it here, but the point is this is the config file to run the paper in the cloud. You just have to put in your own Amazon key. So the idea was we actually assembled the virtual machine that would enable anyone to boot into the paper and rerun the analysis. It would cost you. That's the one thing we didn't do, was we couldn't pay for anyone else to run it, but at least the VM was there. If you logged in with your Amazon account and credentials, you could boot into it. And in fact, we made two versions of the paper basically, or the notebooks. One that would run on it because it was a parallel run that would run on a the smallest multi-core, multi-node cluster that you could build that would cost you, I don't know, the price of a cup of coffee to run it. It would be the real code just on a teeny subset of the data. And then if this was really your field of research, and you want to do the full run, it would cost you a couple $100 effectively of Amazon time at the time. You'd have to spin up about a 30-node large cluster and run it for about 24 hours nonstop. But the point is, if that is your field of research, if you're going to put a postdoc on a project like this for 2 years, spending $200 to validate something is peanuts compared to the time that you would waste even trying to check if things make sense or not in the results. And that same group now actually publishes their papers completely as entirely executable artifacts. So this is from the same group, but last year, a new paper that they published, I wasn't involved with this one, and now they're kind of, I would say, honoring what David Donahoe said, which is the notion that the glossy paper, the glossy Nature paper is just the advertising, right? It's kind of the sales brochure, the thing that real estate agents put out outside the houses, right? The little printout of the pictures. And the real thing that you want to see if you're going to buy a house is you want to see the big binder, right? That has all of the inspection reports and everything, where the sewer lateral goes, etc. That's what really matters. It's not the little one-page brochure. And that's the actual full GitHub repo that has all the code, that has all the analysis, that has all the notebooks. Where did every plot, figure, and table in that paper come from, and how do I replicate that? And so this is now becoming sort of the standard practice. And in the last couple of years, a team who was originally led by Jeremy Freeman, who was originally at Genelia Farm, he's a neuroscientist, and he's now the lead for the biotech side of the Chen Zuckerberg Science Initiative here in the Bay Area. That was announced last year. Some of you may have seen that. Jeremy and Andrew Osheroff from his lab created a project called Binder. And what Binder does is it gives you one button, one URL where you can plug in the name of a GitHub repo that has notebooks and that declares its dependencies. And it will go out, it will Dockerize it, it will build the Docker container for all of the Jupyter machinery, plus that repo with the notebooks and data and everything else, plus your dependencies, and give you an executable URL so that you can share basically the work with anyone, and he actually does pay for it. So out of his grants, he pays for it. It's a free service, so the actual execution capacity is limited, but it does show that it's possible to expose basically single-click executable versions of the scientific literature, which is sort of the path from David Donahoe to our 2012 example to now. And this is being used actively. Some of you may have heard that gravitational waves were detected. We've already had 3 significant events that have been published, and the LIGO collaboration that works on the detection of gravitational waves now publishes their data. They've always had a very open science policy, and they publish their data by giving you, in their Open Science Center, this is really annoying, in their Open Science Center, they actually provide links that not only show their data and the analysis rendered as a notebook, they actually give you links to execute those notebooks either on Binder or actually also on Azure, because Microsoft also has a hosted service. The difference is that the Microsoft one, you have to log in, but it has the advantage that it's persistent. You can actually save your work. Binder is a 0 login, no credentials needed, but it's also completely ephemeral, right? The moment you log out of that Binder container, it disappears. That Docker container gets reaped. And the LIGO collaboration now keeps, so the most recent event, which was published just a couple of weeks ago, it's a noisier and lower SNR event than the original one that made the headlines, or the big headlines a year and a half ago, is still published in the same manner. They actually offer their notebooks officially as a fully executable entity that you can run. That was the sound of 2 black holes colliding 3 billion light years away. So if you actually go there, you can see the notebook and you can run it and you can actually play the audio. And obviously we don't hear those, but it is the sonification of the cleaned up, of the highly cleaned up data. In this case, it's actually the sonification of the numerical template that best matches the data. The one from a year and a half ago, you can pretty much play the actual data, and the signal was so phenomenally clean. They were much closer to Earth. They were about half the distance. The signal was so phenomenally clean that you can actually play the data, and it sounds beautiful. But anyway, as much as these tools are used in research, they're also having a big impact in education. And again, it is a world where many languages will be in play. People using Jupyter are writing, basically using them as companions to books. This machinery is being used to support basically the publication of executable materials, not just research papers or scientific results like these, but entire books. I haven't, if there's a Julia book that I should put here that has a big Jupyter component, please let me know, because I would love to. The most recent one in the Python world was this one by Jake Vanderplas, the Python Data Science Handbook, which is a fantastically well-written book. But I do have some Julia links coming up in a second. Folks like Lorena Barba are writing numerical methods courses to be taught online using this machinery. In this case, it is in Python, but not this is an example of a complete textbook in bioinformatics being written by a professor at Northern Arizona University, Greg Capareso, which is offered from the get-go. When you go to the website, not only can you grab the GitHub repo, but he actually exposes the binder link right away for readers to play with the book. But I do know that in Julia, that similar efforts are being done in Julia, and this is a good example again of this notion that the science comes first and the programming languages come second. This is a textbook which is being developed with support from the usual suspects, the Sloan Foundation in this case, written by Tom Sargent and John Stachurski. Tom Sargent is a Nobel laureate in economics. He's professor at Columbia University, and this quantecon.org website provides not only all of the theoretical material, but actually both Python and Julia versions of all of the computational material for the lectures. And there's a Python version and a Julia version of the main stuff, but actually if you go into the notebook archive that has exercises and whatnot, you'll see Python notebooks, you'll see Julia notebooks, and you'll see R notebooks as well. And they're all together, they're all mixed in. And so students and people and researchers will continue using these tools back and forth, and as much as I love the notion that Julia really has a ton to offer to these communities, it will continue coexisting with these other tools. And so I think we need to keep thinking of ways in which that coexistence can be productive and actually enrich kind of the ultimate scientific and educational goals that I think we all have. And I wanted to mention how some of this is actually changing education, and this may be of interest to you. Some of you may know about this, but a fair amount of this is fairly new, so I figured it would be worth mentioning because Julia, I think, will have a role to play in this, though it hasn't yet. This was a question that was posted presented by the Chancellor of UC Berkeley a couple of years ago to a team of faculty to ask basically, what would it mean for an educated citizen of 2020 to engage quantitatively with the world? And the question was not what would it mean for an applied math major, for a physics major, for a computer science major, for a statistics major. The question was about an educated citizen that comes out of UC Berkeley in 2020, right? What should that person know regardless of their field or major? They're going to face policy decisions made by Congress that are based on data. They're going to face the consequences of climate change. They're going to face the consequences of healthcare decisions, all of which are in one form or another driven and informed by data. How should they reason about that? And the idea was it's possible to actually build knowledge and build courses and build frameworks to teach all of our incoming students about quantitative and inferential reasoning if we lower the right barriers and if we offer the right tools. So what this team did was at first was to create a course called Data 8, Foundations of Data Science. You can go to the website, and the idea of this course was to take away the mathematical requirements of probability theory that are typically a barrier for non-mathematically trained students at the beginning, right? It's not, this was designed, by the way, if you look down here, the people who designed this, we have people like Anya Ricari who teaches it, who's faculty in stats. We have folks like Michael Jordan, who's one of the most prominent statisticians in the world. And this was definitely not, these are not people who don't know statistics. These are actually people who have thought long and hard about how can we bring inferential thinking to a broader population. And the idea was, lower the barriers, lower the mathematical barriers at first, and bring a computationally forward approach. but with a deployment where the tools and the environment are so immediate and so accessible that the entire campus can use them very rapidly. And then gradually you build on that. And then you do build the mathematical machinery and the algorithmic machinery and the theoretical machinery as is appropriate for distinct populations. So this Foundations of Data Science course is offered basically as an interactive textbook, which is a big collection of Jupyter notebooks. You can go to inferentialthinking.com and see the book. And as you're paging through the book, you'll see pages that look kind of like Jupyter notebooks, and they have these blue buttons called Interact. You click on them, and it takes you to a hosted version of the textbook. If you have Berkeley credentials, you can just log in right away, and you have a completely permanent hosted version of it running in the cloud. All of that cloud deployment was based on work that originally was done by Jess Hamrick. She just graduated with her PhD here in psychology at UC Berkeley, and just took a job. I don't know if it's public, so I won't give the details, but she's a phenomenal member of the Jupyter team, and she originally had built a cloud deployment of Jupyter for one of the courses she was TAing, and then campus adopted that. And then on top of that foundation, Berkeley now offers a stack of what are called connector courses that basically build on that initial layer and offer now mathematics, data and biology, data and the brain, data and law and ethics, a large variety of courses that now begin extending those foundational ideas into all of the majors of the campus. This has been the fastest growing educational effort at Berkeley. About 1,200 students took the course. This was done with a tiny staff. Obviously, all of it cloud deployed. There's no way you can manage the IT nightmare of installing libraries and packages on the random laptops of hundreds or thousands of students. There's also the accessibility issue. Not all of your students may have good laptops, and so this solves completely that problem because they can access it via cloud resources. They can access it from the library. They can borrow. The Berkeley libraries offer Chromebooks and iPads on loan, so they can use those resources as well. And it has been a phenomenal success. But again, the entire project is not a Python project. There's Python at the bottom, there's R. I just saw David Anthoff come in, and David Anthoff, who's an economist here at Berkeley and member of the Julia community. I believe David is teaching either a connector or a module, including Julia modules in his teaching. I think that's the case, but we can ask him later. And the point is, this big educational initiative is going to necessarily have multiple languages. The statisticians, even though they are strongly building the Python foundation, they're also interested in teaching some of the more advanced courses in R. And this is actually reshaping the entire university. So a couple of weeks ago, we had the announcement of the creation of a new division. This does not happen at places like Berkeley every year. This is stuff that happens every. Last I checked, the new dean was saying that it was, depending on how you count, 1974 or 1994 was the last time something like this was done at Berkeley. And it's basically restructuring the whole university around computation and data. This technology that communities like yours and ours are building is sort of at the heart of it. This is an example of Ani, the professor who teaches Data 8, teaching one of these very large classes. And they're adding it to the entire faculty kind of community. So this is a picture from a workshop that took place here 2 weeks ago, just across this, basically across this this courtyard, where they are now bringing these resources for Berkeley faculty to incorporate these ideas into their own courses and to begin building sort of computationally intensive and computation data intensive educational materials all throughout the entire kind of system, web of departments and majors and minors that exist on campus. If you want to play with it, you can actually, even without a Berkeley account, now you can play with it. So if you go to try.datahub.berkeley.edu, you'll get a login prompt, and if you use your email address as the username and a blank password, you can actually play with the same thing that the students get, which is basically a hosted version of the book with everything. And I would love to see Julia kind of begin to play a more prominent role in this environment. This is based on cloud-hosted versions. In this case, it's hosted by Berkeley on Google Compute Engine and Microsoft Azure cloud resources, but those companies themselves, companies like Microsoft, like IBM, like Continuum Analytics, and Google, have their own hosted platforms that expose the Jupyter machinery to the public. And I realize that in the Julia world, Julia Computing has hosted versions, but there's also, I think, an opportunity to reach a broader audience by basically pushing Julia into all of these platforms that have a very broad reach. I do want to pitch something that just like you guys have a conference, we do too. And so if anyone is interested in coming to JupyterCon and talk a little bit more about the Jupyter side of things and meet folks from other language communities, please come to JupyterCon in August in New York City. And so I think to wrap up, and so that we leave time for a couple of questions, I might spend a minute or two showing you something new. But to wrap up, hopefully it's sort of clear that with initiatives like what we're seeing here, with the flood of data that we have everywhere, with the kind of changes that we're seeing in education, computation and data are going to really have even a more revolutionary impact in the next decade or so than they've had up until now. And communities like yours and the SciPy community and thanks to an umbrella like NumFocus that binds us all together and that provides the community infrastructure. Leah Silent, the executive director of NumFocus, is here. I would encourage you to talk to her. Julia is part of the NumFocus community. Have made a lot of this possible, right? It's not the IDLs and the MATLABs of the world that are powering this. It's actually the Pythons, the Rs, the Julias of the world that are powering this. And I think that Julia has a ton of phenomenally interesting and new ideas. I look forward to seeing many of the talks to contribute, but it will continue contributing in this ecosystem of many languages, and hopefully it'll bring it'll not only grow itself, but it'll bring a lot of innovation and change also to those other existing communities. And so very quickly, at least to show you kind of what it looks like, and we'll see how the internet behaves. I do have it locally just in case, but this is an example of what it looks like to go to Binder. Let me actually try to open. This is a Binder link. Oops. This is what happens when you go to Binder. Now, this is actually the beta version of Binder, which is we're about to relaunch and scales much better. And that's, you barely got to see this is what the beta version of Binder looks like, because folks at Berkeley have basically been rewriting and updating the original prototype that Jeremy and his team built up to make it be much more scalable. So now if I actually give you that URL, it barely blinks and immediately launches the container, and you can be running any code, any repo that has Julia resources will run in this environment. This is an example of just one of your standard demo notebooks. And now I'm running. So all I had to do was have a URL, and this was an arbitrary repo, right? This is an arbitrary repo. It's not just one of the demos. You can compile the Docker image. What you do is you give Binder here the Docker image and give the GitHub URL. It has to be prepared in the right way, and then it does the building and the spawning of it. And our intent is to basically use this as a way to really lower the barrier for sharing live executable content, and also because it's impossible to have something like this be free really at a large scale. I mean, we can support a small amount of it for free, but it's impossible to do that. The idea is to federate this model based on open standards so that you can imagine a university offers it, a journal may offer that as part of their publication model. A company offers it as part of their services, but it is based on an open standard. So you could say, oh, the free Binder is busy. Let me log in with my Amazon account. Let me log in with my Microsoft account. Let me log in with my campus account. Let me log in with my supercomputing resources account. And then I can be executing that code in this contained environment elsewhere. And so this is an example that at least the Julia version works. I don't want to run through the whole thing because of the usual pre-compilation issues, especially, but it does work. Especially once we start actually getting these guys that want to plot, they take a little bit longer, but you're all familiar with kind of the warm-up issue of the JIT. There are some issues on the Binder repo that UVPanda and Chris Holgraf, the two Berkeley folks who have been working hard on this, they have some questions about basically how to optimize the caching and the building for these repos. So this might be a fun project if anybody here wants to contribute to make this an easier way to expose Julia computations to the world. Please pitch in and give us a hand on that. This is the issue actually. It's on Jupyter repo to Docker, and there's an issue. And I know some folks have already commented from the Julia side. And I think that's it. I'm going to stop here. I think my last slide said, thank you very much. Thank you. I don't know if we have time for one question. Okay, and I don't know if there's anything we can do about the hum, but at least for the other speakers. Yes, please.
Before the not trusted button, the trusted button on the top right in the notebook.
This one?
Yeah, so number one, like, what is it that I'm actually checking to trust it? Number two, in the future, are there works so that the users, can it be done that the users don't have to perform that kind of check?
So when it, yes. What is it that I'm trusting, and are there ways so that the users don't have to trust it? So the issue there is really the power of JavaScript, right? I like to tell people that Jupyter is a platform for weaponized JavaScript, because it was designed to expose, with JavaScript client-side APIs, explicitly execution of arbitrary code on remote resources, right? What's worse than that? That's exactly what your security grandmother tells you to never, never, ever do. And this is exactly what the system is designed to do, right? So it's kind of a problem. And so the notion of what it is that you're trusting is you're saying, I'm willing to let this notebook run because I know to some extent what's in it. It's the moral equivalent of saying you run an installation script. If you run, if you download a binary installer, you have to assume you're letting that binary installer run on your system. A notebook is in effect something of that scope, right? So when you run the code normally and you save it locally, it automatically trusts the notebook and it saves the trust information, the trust signature in a database. We've tried really hard to make this as seamless as possible, but security and convenience are always at odds. There's always tension between those two things. And so this is the case where this is a notebook, because it has been just spawned fresh, it hasn't been run. The system says, I haven't seen this thing and I don't know if you want to trust it or not. Now, we do have a security-specific mailing list for the project. It's a private list, precisely because we want to be able to have conversations kind of openly there, but anyone from the community, so if anyone in the Jupyter community is interested in security issues, please let me know, and we'll invite you to the list. And we've had very significant security reviews by industry teams already of the system. We've had to disclose, we've had CVE disclosures because issues have been found, serious issues have been found in the past, and I'm sure we'll find them again because it's just the reality of the problem we're dealing with. But if anyone is interested in security, let me know, and I'm happy to invite you to the mailing list. Another question?
As for engaging like some layman off the street or whatever and using Jupyter, it seems like the installer is somewhat problematic as far as having to download Anaconda or already have Python on your machine. Is there a plan to make a standalone installer at some point?
So the question was, in terms of kind of engaging people without a lot of technical knowledge, the installation is still a bit of a burden. You have to install Anaconda and this and that. Honestly, we don't have so the question was, do we have plans to make sort of a better installer? And I would say right now we are sort of basically delegating that to the community, because there are so many ways to deliver software, especially because Jupyter is kind of a platform for building other things on top. You do need some extensibility, you need some flexibility, so you really need something that has package management around it, is my thinking. And yes, installing is a burden, but Anaconda's binary installer does give you everything with one click. I don't think we're going to improve on that. Enthought provides also binary installer on the Linux, and those are run on Mac, Windows, and Linux. On the Linux side, obviously the package managers themselves do a pretty good job on the various Linux distributions of keeping it. What we just don't have the resources to tackle. That problem is sort of a black hole, and these companies have put massive amounts of engineering into it. I think what what our focus has been is lowering the barrier with initiatives like this for the web access, which I think has a really big impact in educational context and in research context. For example, Roland Thomas, who just got up from that chair, works at NERSC, and he leads the effort that exposes Jupyter. If you have a NERSC account, if anybody here has a NERSC account, some of you might, it's the Supercomputing Center at LBL, you go to jupyter.nersc.gov, and that's a thing, right? You have access to Jupyter and all of the machinery on the top 6 supercomputer, I guess, in the world now. So we are kind of focusing on the web layer and efforts like Binder as a way of lowering those barriers. And then I think industry is better positioned than we are to lower the last mile binary installer problem.
Okay, that's the speaker again.
Thank you very much, and I'm